Okay, yeah, in that case, we can start with the vectors lesson. So, vectors is your J1 Math chapter 7. So, you'll start on it around August to maybe September, I think. Yeah. And it is a long chapter. There's 3 tutorials inside. But we're not gonna do every single thing. We are only gonna cherry pick certain components of vectors because these vector concepts will be very relevant for the linear classifier that Itin is going to teach you guys on Friday. Okay, so okay, how about before I start, I just get an idea first from you guys. Are there any people who only do bio since Sec 4? So that means you haven't had any contact with vectors from physics or vectors from math in secondary school. Anyone? Okay. Then I guess I assume everyone at least like knows some hand wavy ideas about vectors. So in our in physics, we normally associate vectors as a quantity that has both a magnitude. Okay, let me just write here. A vector has magnitude and a direction, right? So for example, if you have an object, normally you want to draw a free body diagram of an object, you have this weight. The weight has its associated value in newtons. And it also has direction. Direction is pointing to the Earth's center of mass. Okay. Center of mass. Okay. This is physics. Physics vector. For the computer science students normally like to think of vectors as arrays of numbers. So in this case, you could actually model the direction of, let's say if we have a Cartesian plane here. Here is the positive x direction, and here is the positive y direction. Then we could model a vector that points downwards in this fashion as going in the negative y direction. Therefore, the computer science student will probably model it similarly to something like this: 0, -1, where 0 refers to your x values at the origin, and -1 meaning that your y value is -1. It means essentially what you are doing is, if I were to redraw the axis here, we have 0 and -1 here, is you are drawing a line from 0 to -1 with the arrowhead pointing downwards. That's how the computer science student likes to visualize vectors. So here we just have a very simple 2D vector. Okay. For the mathematician, they like to kind of marry both of these ideas. Marry both marriage of both physics and computer science ideas of vectors to represent them with both formats. Okay, maybe just call my English. Represent them in both formats. That means using the Cartesian plane or any other graph axis as a suitable visualization tool, while trying to define some sort of mathematical operations that we can use with vectors so that we can play around with them and we can basically crunch data with it. That's the whole point of us trying to do maths, to make sense of the numbers, in this case to make sense of the quantities that have both they have both magnitude and direction. So in contrast, a scalar, which is like all the numbers that we are familiar with, has only magnitude. Only has magnitude. Okay? So that's the introduction to vectors. Now, if we want to represent a vector quantity, like in questions that you will see later on in August to September, they will represent it as letters like A, B, C, and usually these things will be bold. So actually the correct way would be, for example, for me to do something like this. You will this is how you will see it in questions. Vector notation in print. But obviously when we write stuff, you can't write in bold, right? And that's why if you were to do it in writing, just erase this. If you were to do it in writing, you would have to write the symbol of the vector with a tilde on the bottom. This is the vector notation in writing. Okay? In writing. Let's say that we have a point P and a point Q. And we have a vector A that joins P and Q. This means that we can write the vector as A, or alternatively, we could also write this PQ. So as you can see, right, the arrow is above PQ and it's pointing from P to Q. Both these are ways that we can write vectors in writing. Okay. Okay. Now I shall move on to the difference between. Let me just make the canvas bigger. I shall move on to the difference between position and displacement vectors. Position vector tries to display the vector with respect to the origin O. That means that if let's say we have a Cartesian plane here, x and y. Here we have our origin O. Okay, and we're going to fix a point here at O. We're going to fix a point here, let's call it A. We're going to fix a point here, let's call it B. That means that these vectors, we could call them A, or alternatively, we could also call them OA. Then this vector here, we call it B with a tilde. Alternatively, you could also call it OB with the arrow. So as long as you have, oh, why is it not selecting? Okay, as long as you have this O over here, it means that you're representing the position with respect to the origin O, because you start O is one of the starting points. Okay. On the other hand, if we have a displacement vector, in physics, we learned that the idea of displacement merely tells us which direction and by how far an object is moved relative to another object. So the initial positions of these two objects don't matter. By the same logic, if we were to plot displacement vectors, on a Cartesian plane, all of these vectors, let's call this v1. Okay, and I'm going to copy paste this thing multiple times. Now we shall call this v2, v3, and v4. Realize that all of these have the same magnitude and direction, but they do not necessarily start from the same place. So in this case, we call it a displacement vector because it only tells you the displacement from a certain point to another point in terms of direction and magnitude, where the initial positions of any of the points doesn't matter. So this is position versus displacement vector. So realize that for position vectors, because we are anchoring them to certain points, anchoring one to the origin, anchoring another point to a certain location in the Cartesian plane, we can use the alternative notation, which is like the vertices and then the arrow on top of them. But for displacement vector, we can't because there are no fixed vertices in the first place. Okay, so this is position versus displacement vector. Now, let's go through modulus of a vector. Okay, so let's say we had a vector, we call it A. The modulus of the vector essentially will be this distance, right? You want the length of the arrow represents the magnitude of the vector. So the way which modulus is denoted is by using the absolute value sign. The absolute value sign is sometimes also known as modulus. So that is how a modulus is denoted. Or alternatively, if I were to add a point P, points Q, we also know that we can denote the vector with P, Q, and an arrow. And by extension, the modulus of the vector will also be represented like so. Now, this is a very simple 2D case. I shall introduce the concept of norm later. Okay, never mind. Then, I shall introduce unit vector. Unitary. The word unitary means one. So, you may be able to guess that a unit vector is therefore a vector with a magnitude of 1. Okay. So, in this case, it will be, let's say we just choose this distance. A unit vector is denoted with a hat. Over the original vector symbol. This is not to be confused with typical notations of hat in machine learning, which are used to signify ground truth. Okay, I can just type that. So this is just in the pure mathematical sense. A unit vector of let's say borrowing this A here, the unit vector would essentially point in the same direction as the original vector, the only difference being that its magnitude is 1. Okay, so if you have a unit vector, it also follows that the modulus of a unit vector would be 1. And if we were to find the unit vector from the original vector, we will basically get this relationship where the unit vector is the original vector. It will be the original vector multiplied by 1 over its modulus. So when you receive your math notes later in August, you would see it denoted like so, which can be quite misleading because in vectors, division doesn't make sense. So it may seem weird to divide these two quantities, but just note that this one is original vector, and here is modulus of original vector. So if you think about it intuitively, you have the original, let's see, you have the original vector here. If you divide it by its magnitude, which is the length of the arrow, and you were to create a new vector by just multiplying it against the original vector, you will basically get a unit vector, because multiplication of a vector essentially will just scale it, will essentially just scale it with the direction of the original vector. So speaking of that, let's just jump straight into multiplication. Multiplication of a vector by a scalar. So if I had, once again, I had point P, point Q, so we have our vector here, A, right? Or PQ. Let's say I want to draw 2A. Essentially, we would take this thing, copy paste it. Okay, I would basically grow it in size by 2. I'll grow its size by 2, so basically the double the size is roughly around here. And okay, let's call this Q1. Then we have Q2 here. Then we draw a new line. This is 2A. Okay. Simple enough. If we were to multiply a vector by a positive scalar, we essentially preserve the direction of the original vector, but scale the magnitude by the coefficients. And that's also the reason why it's called scalar, because it scales the magnitude of the vector. Then you might be wondering about minus A. If I multiply a vector with a negative number of -1 in this case, the magnitude should stay constant because you scale it by 1, it's the same. But because it's negative, we actually flip the direction. So what I'll do now is I will just go here, flip the direction, and now we have negative of A, and we have Q1P is equal to the negative of P Q1. So realize that multiplying by a negative number will flip the direction of the vector. Now, what about 0A? What about 0A? If you multiply the magnitude, you scale it by a factor of 0, you get nothing, right? So you can't draw it. Therefore, a special quantity known as null vector or zero vector results. And note that you must draw the tilde here. In math questions, they often like to troll you. Your answer may be a zero vector. Then a lot of people forget to draw the tilde and the -1 mark. Yeah. So these are multiplication operations on a vector using a scalar. So now that we know these multiplication operations, if we revisit this formula, essentially we are just taking the original A and we are scaling it by 1 over its magnitude. So this will give us the same vector in the same direction but of a magnitude of 1. So that's why that's the formula of the unit vector. Okay, so okay, then of course some properties of, here's my pen. Okay. Parallel vectors. Okay, I haven't been drawing lines down here, so I should stop. If we have two vectors, u and v, with the tilde, of course, we say u and v are parallel if and only if u equals kv for k is a member of the real number set and k is not 0. Alternatively, we could write it like this: exclude 0. Okay, so using the same logic, it means that u is essentially a scaling of v along its same axis, and and so there's parallel vectors, and this thing may come in useful later when he teaches linear classifiers. Okay, and now the next thing I'll go through is vector addition.
So still parallel with k.
Sorry?
Two vectors still parallel with k.
Two vectors still parallel. What?
The k is negative.
If they are negative, yeah, it's okay.
Always good.
Because like the directions are, even though the directions will be opposite, but you see they're on the same axis.
Yep.
Okay, I should write that. Holds true even if k less than 0. Okay, so now we go to vector addition. So if, let's say, we had a vector a and we had another vector b, how am I supposed to add these two? If we add it by tip to tail method, essentially what I'm going to do is I'm going to take this guy, whack him here. You see right here we have the tail, tip of vector. Here I'm going to take this guy, and then I'm going to place the tail of B at the tip of A, and then I'm going to draw the resultant as such. Resultant being A plus B. Okay, so that's how you do vector addition. But let's say if our things, okay, wait, no, I won't go there yet. Then after we've done vector addition, now we do vector subtraction. So again, if we have A here, now instead of plus we're going to do minus. B, what we're going to do is we're going to express this as an addition. So remember, negative would actually flip the direction. And therefore, I will actually flip the direction. Realize that A minus B is equal to A plus minus of B. So once we re-express it in terms of addition, we can again use the tip to tail method. Then we just align like so, and our resultant is here. Oh, my drawing failed. Okay. Similarly, if we do vector subtraction in relation to position vector, let us revisit this example. This dude. Okay. Yeah, boom here. I am going to stop using the A tilde. I'll just call this OA. I'll call this guy OB. Okay. What if I wanted to find this vector? Oh, I cannot draw straight lines, but never mind. What if I wanted to find this vector? Realize that actually AB is equal to OB minus OA. Because if we were to prove this, we are actually, if we were to prove this, just copy this, okay? OA. Imagine you move OA down here, then you flip the direction of OA, minus OA, then your resultant will be here. And because there's no O here, there's no O in this notation, therefore it's not anchored at the origin, right? That means, what is it? It's not a position vector. It is a displacement vector. It can go anywhere. So AB can go anywhere, right? And that's why you can actually move this guy up here. They are the same. They are one and the same. So that is the proof of AB equals OB minus OA. I'll just put this here, call it proof. Okay. Yeah, that's correct. Okay. Yeah, so that's vector subtraction. Okay. So now properties of vector addition and subtraction. So if you have A, if A is a vector, then you also have lambda A is a vector, because lambda is just a scaling along the same direction. Lambda of mu A is equal to lambda mu A. This is pretty badly drawn. This one is quite simple to understand. Lambda plus minus mu of A is equal to lambda A plus minus mu of A, and lambda of A plus minus B is equal to lambda A plus minus lambda B. So here you have distribution of scalar multiplication of vectors holds true. Okay, this distributive property. Okay, having said that, now I shall go into trying to represent vectors on the Cartesian plane. Consider, actually there should be a tool to draw never mind. Consider a vector. Let's call this A. We have our origin here, okay? Let's say we have a vector, okay, it's not straight. We have a vector OA. It's like this, okay? So we have OA. Now, let's say that this A, right, actually is a coordinates of x comma y. So here is going to be x. Here is going to be y. Then let me okay, let me just switch colors. Let me further define two unit vectors. Okay, unit vectors that have magnitude 1. We call this I hat, and we call this one j hat. Again, both of them are unit vectors, and they have magnitude 1. The special thing is that I hat is a unit vector that points in the positive x direction. J hat is a unit vector that points in the positive y direction. Then we can actually express OA as such. Agree? Because x is the x coordinate, it's a scalar. Y is the y coordinate, it's also a scalar. Scalar multiplied by vector gives you vector. Scalar multiplied by vector gives you vector. See? Here, vector plus vector. So essentially, it will be x times I hat. It will give you the vector pointing along this direction. And then you plus y times j hat. Then your resultant will be this red line. So we call this the Cartesian form. Of the vector, and it's very aptly named because, of course, you are trying to represent the vector on the Cartesian plane, and therefore we call it Cartesian form. Okay, so you can also say that OA equals big bracket x on the top, y on the bottom. This is another way to write it. This one is called column vector form. Cartesian form of OA. Okay. Then, if let's say I'll just call this A. Then, if you want to find the by Pythagoras theorem, we can also derive that the modulus of A is equal to the modulus of OA, which is equal to root of x squared plus y squared. Pythagoras theorem, simple. And that will also mean that our unit vector A hat is equal to, remember, original vector, scale it by 1, the reciprocal, 1 over the magnitude, which is given by the modulus. So it will give us 1 over x squared plus y squared A equals 1 over x squared plus y squared x y. Okay. Yeah. If we were to extend this to 3D, so okay, let's just write 2D. If we were to extend this to 3D, it would essentially be the same story. X plane, Y plane, this goes up to get here, and Z plane. This is not the best. Okay, Z plane. Let's say we have a point here, call it A again. A will drop down. certain z coordinate, a certain x coordinate, and we have a certain y coordinate. So I'm going to draw a box like so, close the box, then we have our O here, right? And I think we just connect here. So we have our vector here. Then in that case, we are going to again just change color. We're going to define our unit vectors. Here we have I, hope this will be close, I tilde hat. Here we have j tilde hat. Here we have, now in the z direction, k tilde hat. So these I, j, k are the unit vectors that by convention people like to use to represent the unit vectors pointing in the positive x, positive y, and positive z direction respectively. So again, to copy this structure, it will be OA is equal to x times I tilde hat plus y times scale the j plus scale the z. Okay, this is Cartesian form. Alternatively, you want to put it in the column vector form. You get like that. Then again, call this A. Okay, so I'll call this A. Then by Pythagoras theorem, x squared plus y squared plus z squared. Okay, then if we want the unit vector, then we take original vector, scale it by 1 over modulus, so it's 1 over x squared plus y squared plus z squared a, which is 1 over x squared plus y squared plus z squared of x, y, z. Okay. So in this case, okay, let's just copy this diagram again. In this case, let us change color once again. And we go here. Here is x times I hat, and here we have y times j hat. So we also have a special name for this. X I hat and y j hat, called component vectors of A, and similarly in 3D case it will be xi, xi, yj, and zk. Okay, so if I were to go and express I, j, and k in column vector form, it will be like so. Makes sense, right? It means one unit in the positive x direction, nothing else for the other two x's. One unit in the positive y direction, nothing else for the other two x's. One unit in the positive z direction, nothing else for the other two. That's for 3D case. Okay, I should move this here. And for 2D case, we have I hat equals to 1, 0. J hat equals to 0, 1. Okay. Then here, let's use paste here. These guys, again use color. Here we have ZK. Here we have XI, and here we have YJ. Again, these are component vectors. Okay, so there's some basic vector math. Okay, then oh yeah, also if you were to do the column operations on the column notations of vectors, then if you have x1, sorry, if you have x1, y1, and z1, when you add a x2, y2, and z2, it is basically doing this. This is analogous to adding the components on the Cartesian plane. So the way in which you can visualize this is, if let's say I have is basically like x, y. Okay, I'll just use a smaller point here, a. Then if I have x1, y1, here x1, and here we have y1. Then if we add on another x2, if we add on another x2, if we have let's say we have x2 over here, okay, and then this is a point B. Okay, maybe I'll probably, okay, how about we move B closer inwards so it's easier for you all to see the difference. This is quite messy. Okay, I'll just erase this. x1, y1. Okay, and here x2, y2. Then B is here. Right? Then if you want to add these two together, vectors together, it is equivalent to summing their two components together. So essentially what we're gonna do is, let me just move these elements. Move this guy as well, so it doesn't block anything. Essentially, what we are trying to do here is x1 plus x2, y1 plus y2, okay? Here we have x1 plus x2, and here we have plus y2. Okay? Yeah. Then basically your resultant vector will go like that. So that is a plus b, like so. So that's essentially what this line is saying. Okay, and similarly, if you take a lambda times x1, y1, c1 is equal to multiplying lambda inwards. Zero values included. Okay, so this is 3D case. The same goes for 2D. So that's some that's a basic vector math. Okay, so okay, so that's like just the introduction. So now I'll need to introduce a very important concept, which is called scalar product or dot product. Some of you who read up on vectors may have heard of another type of product called cross product or vector product. I'm not going to go through that today because in ML you usually don't don't see don't use that don't use that form of product. So usually only use scalar product in ML equations. That's why I'm only going to teach that here. Scalar product, also known as dot product. So let's say we have two vectors a and b, and they're separated by an angle theta. Okay, the dot product is defined as vector a dot of vector b. So you see this dot here is magnitude modulus of a times mod b. Whoops. Okay. B times cosine theta, where theta is the angle in between a and b. So how to visualize this? If you recall, right, let's say we have a right angle triangle. Okay, x, y, and z. You have theta here. So so if you want to use the sine, cosine, and tangent rules, essentially it's like sine theta is equal to y over z, right? Therefore, if let's say you don't know y, then y will be z sine theta. Then if you let's say you don't know x, right? Then cosine theta is equal to x over z, adjacent over hypotenuse. So x equals z cos theta. So if we were to bring that logic here, actually, right, if we were to drop a right angle triangle down here, this will mean that here, right, this vector here, the magnitude of this vector will be b cosine theta. The magnitude will be b cosine theta by applying the same logic. So if we take a dot b, which is a times mod a times mod b times cosine theta, we are actually taking the magnitude of a, so like this whole thing, times this thing. So that is like a kind of a nice way to visualize it. So you just write it down. Therefore, A dot B is like magnitude of just delete all these extra elements. Okay, magnitude of A multiplied by just the red portion. Okay. So it's here multiplied by here. That's dot product. Okay. Then the angle, right? The angle theta, it depends on the definition of angle theta depends on the orientation of the two vectors. So okay, different orientations of A and B. So if we have, let's say if we have like A and B like so, then what we will get is like this. You can put them together. This is our theta. Or you can move. You can okay, actually it will be better to copy paste this. It will be, you do like this. Okay. Just move this down here. Then you move the V up like that. And here is the theta. So you just redo this example. Here, take this guy, and I take this guy, and then we don't touch. Oops. Okay. Then here's my theta. Then if let's say A is like that, B is like that, what we are going to get is, first way, I put this guy here, then I put this guy here. So like so. Okay, actually I'll categorize it here for good reason later. The second way is for me to put this guy here first, then put this guy here. Okay, let's just move the A out here to make it easier to read. Okay, all these thetas are all the same. So realize here, right, the A and B converge at a point. Here, A and B diverge from a point. So yeah, so we could draw a line that splits them like so. Yeah, just put it all in the middle. Okay, so that's how the dot product works. Then there are some pretty important results regarding the dot product. So this one will be very important for linear classifier. Let's just write properties of dot product. Let's say A is equal to x1, x1, y1, z1. B is equal to x2, y2, z2. Actually, there's no need for commas. Sorry. Okay. Then A dot B is actually what you do is x1, x2 plus y1, y2 plus z1, z2. If you think about y, graphically, if we go back to, let's say this, if we go back to our Cartesian representations, remember the whole idea of the dot product was to use the cosine theta such that you could bring one down to align with the other, and then afterwards you make the multiplication, right? So if we already express our vector in Cartesian form, realize that for the 3D case, we already have three component vectors that are along the I, J, and K axis to deal with. And that will mean that we already have three components that are all pre-aligned with each other. And that is why performing a dot product like so results in element-wise multiplication, like so, of the individual component vectors of the two things that you want to multiply together. Okay. Now, so this is the first one. This is the first very important one. Then, if let's say we had an A like this, and a B like this, and they are orthogonal to each other, perpendicular. Now, we know from y equals cosine x, your graph is there. It is a very terrible cosine graph, but yes, here we have 0 degrees, here we have 90 degrees, right? Here we have 180 degrees, 270 degrees, 360. Okay? So, if we were to take A dot B, right, for this case, it will give us mod A mod B cosine 90, and we know this to be 0 because of this relationship, and therefore we get 0. So actually, right, if A is perpendicular to B, A dot B equals 0. And this is actually like a definitive test for perpendicular vectors, orthogonality. And notice that here, it is 0 without a tilde on the bottom, because if we look back at the definition of the dot product, here you have a scalar, because the modulus gives you a scalar. Here you have a scalar. Here you also have a scalar. So scalar times scalar times scalar results in scalar. That's also why we call it scalar product, because the result of this multiplication operation is a scalar. That is also the reason why here I've written a 0 with no tilde. So it represents a 0 scalar, not a null vector, not a 0 vector. Okay? So that is if these two are perpendicular. Then, if let's say we have a A and we have a B, and the angle between them is 180 degrees, then A dot B equals, and we know that this is -1. So this will basically just give us negative A, B. Okay? Now, Okay, then if we were to go back to this relationship, right, this would also mean that cosine theta equals this is merely there's a shifting of this guy down to the denominator on the left hand side. So if the dot product is known and the magnitude of each vector is known, then you can easily find out the angle that exists between them. Okay? Okay, then more properties include a dot b equals to b dot a. Why? Because okay, I can for these important properties, okay, okay, before I go down here, how about I write another line? If A and B are in opposite directions, A dot B equals minus. Okay, so let's cross this guy up. Then A dot B equals B dot A. How do we visualize this? Let me just just make the canvas bigger. A dot B we have visualized it as such, right? Where the distance here is. These two B dot A dot B, so here is A, here on the left hand side we have mod A times B cosine theta. Then here we have mod B times mod A cosine theta. Essentially, it is taking the same thing, just that you look at it from this perspective. Oh shucks. Okay, then you take here, you drop. Then here, the vector, where the distance here is A cosine theta. Okay, both of them are going to result in the same thing because you are essentially just flipping these two around, which changes nothing. So there's this equality here. Okay, A dot 0 null vector give you 0 because the magnitude of a null vector is 0, and therefore that happens. You get a dot 0 equals 0. Okay, then next one will be a dot a. What happens if you dot a vector on itself, right? So let's see if a, and you just find a dot a. If we sub in the formula, cosine 0 degrees. Okay, I realized that I've been forgetting to put my degrees. Oh no, I actually put it there. Yeah, so we know that cosine 0 degrees is 1 from the cosine graph. So this actually gives us the square of the modulus of A. So this is also another important relationship. A on itself, dot itself, gives you the square of the modulus. Okay? And afterwards, okay, then if you want to do lambda times a dot b is equal to lambda a dot b which is also equal to A dot the lambda B. Of course, lambda is a real number. So this one, you want to prove this, you can easily just do it by expanding the formula. Okay. Similarly, MA dot NB equals to MN A dot B. All these are all can be derived from the original formula. Okay. A dot B plus C is equal to A dot B plus A dot C. Okay. So because this one works because if you think about it, B plus C gives you the resultant vector. The resultant vector, if you add B and C, then by dotting it with A, you are taking that, you're dropping a right angle triangle, and you are making a line with A, and afterwards you multiply the magnitudes together. Similarly to what I've done. So that's akin to doing the exact same process but for each vector and summing results together. Okay? And of course, if you have A dot B equals to A dot C, does not mean that B equals C. Okay. No, cancellation doesn't work for vectors. Okay. Does not mean B equals C. Okay. And lastly, A dot B dot C is meaningless. Oh, this is in red color. Because the very idea of the dot product, you can only dot two things at once. How does one do a triple dot? It doesn't make sense. So you would and anyway, the product of A dot B is a scalar. You cannot dot a scalar with a vector. You need to dot two vectors together. Okay, so that thing is meaningless. Okay, so now it's 5:47. I think we can probably take like a 10 break. Then I will go into projection vector and plane, because plane is an important concept for linear classifier. You need to draw a plane for a linear classifier and see whether the points lie above or below the plane for you to classify them. Okay, so yeah, I'll just temporarily stop sharing first, and we go and take we come back at like 5:55 like this. Okay, so now we're gonna go over to concept of projection vector. Okay, so let's say that we have a line here. Okay, now let's call this a vector, direction vector called D. Okay, and here we have the origin O. Here we have a point N, and right above the point N, I'm going to define another point A. And I'll draw my vectors. Oh my god, this is so complicated. I'll draw my vector A like such, and then you're gonna drop a right angle triangle here. Okay. Then I shall not call this B. I shall call this B. Better to call it B. So earlier on, when we were looking at the dot product, I introduced you all to the idea of kind of dropping a perpendicular line down here, and then using the cosine theta to find this distance, right? This magnitude. So very similarly, it's tied to the idea of projection vector. So essentially, if I were to find the projection of A onto B, so let's just move this down here. Find the projection of A onto B. Okay. Essentially, it is going to be this length ON. A onto B equals ON. Okay, this is theta here equals mod A cosine theta and mod A cosine theta equals mod A times. Remember, because once you have the hat here, it means that it's a unit vector. So magnitude is 1. So I am essentially forcing out the formula of the dot product. Equals A dot B hat. So why does this make sense? If you think about it earlier, the way in which we calculated the dot product was by dropping a foot of perpendicular down here. Then we know that this line, this one, gives us the length of this thing is A cosine theta, right? And that will mean that if we multiply this times 1, it gives us this length, which is exactly what we are achieving here by simply multiplying it against the magnitude of the B hat, which is a unit vector with a magnitude of 1. So this gives us the projection. This gives us the length of projection. Okay. The length of projection normally in this case is correct. So because the scalar product is vector dot against another vector, so it gives us a scalar. But in the case where, let's say, if we take A and then we put it on the other side, and then we bend OA such that this angle is obtuse, then your projection will actually point in the opposite direction. So that's why usually we define the projection vector projection length as the modulus of A dot against B hat, because you just want the length. You don't really care about the direction. So you put a modulus there such that even if your line here was angled this way, even if your theta was obtuse, you would still end up with a positive projection length, which is what you want. Okay? Then if you want projection vector, so here's length, right? So realize this is a scalar. If you want a vector, A and B, this is essentially A dot B hat in the direction of B hat. Okay. Remember, here we're finding a projection vector. That means on the right hand side, this entire thing needs to be a vector. So we know that here we have a unit vector of v. So that's the vector component. Meaning that whatever is over here in front is the coefficients, the scalar multiple of the vector. In this case, notice how I use round brackets, because once you try to find a projection vector, then that will mean that the direction is important, because you're trying to find a vector. That's why I don't use the absolute value sign. I use a curved bracket. And this constitutes the coefficient of the vector. And then here you have the actual vector itself. So let's just draw that in a neat way. So one part here, coefficient is basically the length of projection but with direction taken into account. Here we have unit vector of B essentially provides the direction component. Of the projection vector. So this that means the former part provides the magnitude component of the projection vector. Okay. So that's projection vector, done deal. Now I'm gonna skip all the way to near the end of the vectors chapter, and I'm gonna talk about planes. Okay. We start again with plane pi, origin O. Point A, point R, not point B, sorry. This is a better way to put it. Let's join these lines. Okay. Then we assume that we know two things here. Two displacement vectors that we already know to lie in the plane. So they are not parallel, and that will mean that if you want to get the point, or if you want to get a point of any point, you want to get the representation of any point on this vector plane, then you could essentially create it from like any combination of B and C. Because for example, if C is like that and your B is very short, then you get this point. If your B is very long, you get this point. You could also vary the direction of C, you could vary the direction of B, and basically because your coefficients of C and B can take on real values, that will mean that you can mix and match the coefficients to give you any single point on the plane. So let's say you want to call this point B. You want to call this point B such that if you point it back to the origin, then vector B. Okay. Then it follows that V equals lambda of B plus mu of C, where lambda and mu are real numbers each. Okay, my bad earlier. Okay, this is the correct one. Okay. Then now we suppose that the plane contains a fixed point that we know to be inside the plane. We call this fixed point A. And A has a position vector of small a tilde because it's rooted at the origin, right? So then if we consider another point R that's on the plane, then we know that R equals A plus, so it's like here, you go here, you go here. So that gives you R, right? Since we know that AR, okay, any point B, any point on the plane any point on the plane pi, B can be expressed as like this. Then
But are B and C vectors on the plane? Like, are they contained in?
we assume that we know that they are already on the plane.
The vectors are like contained in the plane.
Yeah. They are displacement vectors. Because remember, displacement vectors technically you can move them around anywhere. Only the direction and magnitude matters. So even if they're not outside, we can actually easily move them inside and they'll be considered to be part of it. Yeah. Okay. Consider a fixed point A that lies. Okay, no. Consider two fixed points. No, consider a fixed point A that lies in pi. Then consider a variable point that's capital R. Then you get this relationship. That one's simple enough. Then since AR lies on pi, because you can clearly see from this diagram, AR is also inside the plane of is inside the plane pi. Therefore, you have equals A plus AR, and because AR lies on pi, we know that we can borrow this earlier relationship, which describes any point, describes any point on the plane, and we can essentially just sub it in. So essentially you can the way in which you can interpret this formula will be, if you want the position vector R of any single point on the plane, first is we go from the origin to the known point A. Then afterwards we take any linear combination of B and C. It could be like that, then we end up with a point here. Alternatively, it could be up here, it could be down here, and then we end up with a point over here. So the idea is that first we move from the origin to the known point A, and then we just take any old combination of B and C, and then we can get every single point on the plane. So if we take all the real numbers, we take all the possible real numbers of a lambda and a mu, and you dot space, then the shape that you will eventually form is this plane. Does that make sense? If anyone is confused by this notation, then just let me know. Okay. So this is what they call the parametric form of a plane. Why parametric? Because parameter. Here, you have these two parameters that you can vary to give you different points on the plane. That's why they call it parametric form. An alternative way in expressing the plane pi would be, let's say now they give you the equation of let's say they gave you a vector n that you already know is perpendicular. Okay, just draw these two right angle squares to indicate that this n is perpendicular to the plane. So we call this a normal vector to the plane. N, that's rather messy. N is a normal vector to the plane pi. Okay. Then just make the canvas bigger again. Okay. Then we do the same thing. We define an origin here. We define a known point and define a variable point. So here we have our A, and here we have AR. And then here we have our R here. Okay, so remember, if two vectors are perpendicular to each other, their dot product is supposed to be 0. I will just scroll all the way back up. Here, this relationship. If they are perpendicular, the dot product is 0, because the cosine of the angle between them will be 90, and that evaluates to 0. Okay, so if you scroll down, now we know that AR lies in the plane, and because AR lies in the plane, it is automatically perpendicular to this normal vector n. Okay, so AR dot n is 0. And if you look at AR, remember by the earlier relationship, let me just go back again. Where is it? The one with, okay, here. The one with vector subtraction. If we have a vector AB, right, AB is equal to OB minus OA. So you take O and then you look at the last letter and then you minus with the first letter. So that's how you evaluate it. So now we go back here. AR will be OR minus OA. 对吗? Dot n equals 0. And because we know OR is equal to this guy, so that will give us R tilde minus OA, which is equal to this guy. So we can sub it in like that. Okay? And earlier on, we also had established the scalar product property, where if the scalar product is outside, right, you can actually apply the scalar product to each element inside the bracket. So equals 0. Essentially, I'm gonna do like the rainbow rule like this. We can do this because we stated it earlier, and if you all want to prove, you can easily prove yourself. And realize that we define this to be a fixed point, and define this to be a variable point. R can move, A cannot move. We define A such that it cannot move. If A cannot move, that will also mean that this guy here is a constant. If this is a constant, and we also know that n is a constant, it means that this entire thing is a constant. So I'm just gonna move him to the right hand side, and because we know it's a constant, is also a scalar. I'm just going to collapse this guy into a constant d. This right here is the scalar product form of our plane. Okay? And if you look at this formula, r dot of n gives you d. It actually kind of makes sense, because if let's say you were to take this vector r, you can just copy here. You take this vector r and we position it like that. Similarly to how we will calculate our dot product, we have to drop a right angle triangle, and then we will basically be taking this distance, right? So alternatively, I could like extend the normal infinitely, and essentially what this equation r dot n equals d is saying is that if we take any old vector, as long as it lies on this plane, right? If I were to take the vector and I were to dot it with the normal, if I dot it to the normal, means that I will drop right angle triangle and then I will align it with the axis of the normal vector. The result will always give me a constant. And that means that no matter where I put the vector, right, it will always maintain this certain distance from the start point. And that is essentially drawing out the shape of a plane. So I can explain one more time. If we were to take any point on the plane and we were to draw vectors from the origin to those points, and essentially when we are taking all these R2, R3, and then when we dot it with the normal vector, we are moving it like that. We are moving the vector like that. Then change color. Then we actually this is in 3D. So by right, it should be like you should be having a triangle that points out of the plane of paper. And essentially we are taking this distance, right? This distance will give us, this is the distance of r dot n. And if we set it to a constant d, it means that we must find the collection of all the possible vectors, such that when you drop a right angle triangle and you try to project it onto the normal vector, it will always give you the same distance. So if you think about it, this would give you the collection of all the possible points, such that it will maintain the same vertical distance when projected onto the axis of the normal, and that draws out the shape of the plane. If it's difficult to visualize this, yeah, don't worry, because for me also I took around a few months. No, sorry, I took around a few weeks to understand like what this r dot n equals d actually meant. So you can always review the recording later, and I'll also be publishing this whatever I've drawn here today on the slide, on the Google Drive, so you all can refer to it later. Now, if I were to take this one step further by defining this, so you realize it's very similar, right, to the top equation. The only difference is that now we are using n hat. That means that we are defining the normal vector as a unit vector. So all we want is a unit vector of magnitude 1 in the direction of the normal, of the plane. And we repeat the same process. We find the collection of all of all the possible lines such that when we dot it, all the possible lines such that when we dot them onto the unit vector of the normal, it will always give us the same distance. So the special property with this equation is that now this small distance d represents the orthogonal distance from the origin to the plane. Because if you think about it, right, once again, this line here that I just drawn is essentially analogous to this normal vector, because we can always just take the normal vector and then shift it down here. It's the same thing because it is still perpendicular to the plane. Then if we have all sorts of vectors that are emanating from the origin O, then we dot it onto the normal vector. Once again, we are essentially like dropping right angle triangles, right? We are all dropping right angle triangles. And then we are forcing this distance to remain constant, and that will essentially draw out the plane if you consider all the possible arrowheads that can give us this configuration. I know this one can be quite confusing. It's also really darn confusing for me. So what I'll do is I'll also upload like the pages of the math notes from chapter 7 that clearly, again, in formal language, explain these two equations. So this small d here is the distance, perpendicular distance from plane to the origin. Okay. Yes.
Wait, so the small d, right, is also equal to a times n, is it?
Sorry? No. Because remember, right, n hat is equal to n divided by, it's not really divided by, n scaled by the reciprocal of the modulus of n. That means that actually, right, if I were to put this here, if I were to put it back here, it will mean that it will be like that, right? Then if I were to take this guy and throw him to the right side, it will become like that. So this guy here is the big D. Does that make sense?
What does n hat and like n equal to again?
The hat means that it is the unit vector. It means you preserve the direction, but the magnitude is fixed at 1.
Oh, okay.
And the reason for doing that is such that when you try to find all the possible arrowheads that lie on the plane, and you dot it, so you draw the right angle triangle, and you project it onto the normal vector. You want the n to have a hat such that when you do the dot product, right, you multiply it by 1. Then you don't change the value.
Okay.
Yeah.
Okay.
Yeah. Okay. So that's pretty much it for planes. Then now I will just give a very quick preface. Okay, I know it's getting 6:31, so I'm going over time already. But let's bear me for like 5 more minutes. I will basically give y'all a quick preface to how all this knowledge of planes, knowledge of projection vector, knowledge of scalar product, and basic knowledge of vectors can be applied to machine learning in the case of linear classifier. So it's a preface to what ET will teach you. So essentially, okay, once again, make the canvas bigger. If I have a Cartesian plane xy like that, and we just imagine, okay, because the Cartesian plane is 2D, we just imagine the plane is extending out of the plane of the screen, outwards of the screen and into the screen and out of the screen, okay, extending infinitely. So let's say that we have a normal vector, we call it Q, center and origin. So this will mean, by extension of what we've learned earlier, this will mean that the equation of the plane is, okay, I'll just use r dot q equals 0. Or to make it friendly, it will be like this. To use the same symbols as earlier on, is 0. Remember when we use this formula, the thing on the right hand side represents the orthogonal distance from the plane to the origin. So if it's 0, it means that the plane is directly cutting the origin. So if we now consider a point, let's say here, call it D1, and the point here, D2, okay? That means that we have vectors like so. So D1, ooh, that's messy. D1 and D2, like so. Okay. Just define that. Okay. This means that by actually comparing the value of D1 dot n versus D2 dot n, you can actually tell if the point lies to the right or to the left of this plane. Okay. Comparing like this. You can tell if the point D1 or D2 lies to the left or to the right of the plane. So for D1 case, or D2 case, so we know that here we have, it looks something like this, right? We have our D1 here, then we have our n, our normal vector. Here is our theta. For D2 case, it looks something like that. Okay, maybe not so 夸张, but something like this. D2, and we have our n here, and here is the angle in between. Realize that here, theta is less than 90 degrees, here theta is more than 90 degrees, obtuse. Acute, obtuse. Therefore, cosine theta greater than 0, therefore cosine theta less than 0. Then, by looking at the polarity, positive or negative, we can actually tell left or right. So, this would imply that D1 dot n would be greater than 0. This would imply that D2 dot n is less than 0. Okay, so by looking at the polarity, you can tell this left or right. Side of the plane.
Is n a vector that's perpendicular to the actual line you're using to split?
Yeah, the red line, you can think of it as a plane. So like the plane it extends infinitely outwards, out of the screen and into the screen.
Mm-hmm.
Yeah.
Oh. Okay.
Yeah.
And N is like normal.
Then N is the normal, so it's analogous to this dude.
Oh, neat. Thanks.
Yeah. So realize that if let's say we plot, right? We plot here. Oh, that is messy. Okay, here we have 90 degrees, 180 degrees, 0 degrees. Then we can reproduce this graph on the other side. Minus 90 degrees, minus 180 degrees. Here you have positive, here you have negative. Right, see in this region, all positive, and in this region, all negative. And the way which we can visualize this is if we have our plane here, assuming that the plane extends infinitely outwards and infinitely inwards, then we have our orthogonal vector n. Let's just call it that tilde. Okay. Then we have our 90 degree sign here. So here it will be choosing like we'll be choosing D1, D2, D3, and D4, such that here you have acute theta. So here we have a 0 theta 90. Then over here we have, we can define it. We define this direction. No, the theta is here. Sorry. So in this direction, in the anti-clockwise direction, we define the angle to be positive. In the clockwise direction, we define the angle to be negative. So it will be minus 90 is less than equals to theta, less than equals to 0. Then let me just move this guy, redraw him, D4, go outside so it's easy to see. Okay, then if we were to, let me just go to the blue pen to see, realize that now we have 90 degrees less than equals to theta less than equals to 180 degrees. And if I were to oh no, red pen is wrong, should be blue pen. To drop an angle here, it will be minus 180 degrees less than equals to theta less than equals to minus 90 degrees. So now if we look at the red region and the blue region, realize that D1 here is the region of D1, here is the region of D2, here is the region of D4, and here is the region of D3. So any single angle around the plane, you can infer the side with which the point lies. So this is like the preface to the linear classifier. Okay, and the one last thing before we go would be, if we go back up to the Pythagorean distance when I taught you all the modulus of a vector. Yeah, this modulus of a vector, this thing where the modulus of vector is defined as x squared plus y squared and then square root of the whole thing, right? So in machine learning literature, you will often see a notation like this. Sometimes you see like that. Which is L2 norm of A. Okay? This is similar to this thing. This thing that we talked about in the beginning of the lesson. So Yiqin will be using words like L2 norm. He'll be throwing them around when he teaches you a linear classifier on Friday. So to recap, today we went through the linear regression project. We went through the Marcus report for that. Then for vectors, we introduced vectors as quantities that have both magnitude and direction. We went through some very basic properties of vectors such as the modulus of it, which is the magnitude of the vector, the unit vector, which is the same thing, just that the magnitude is 1, scaling of vectors, flipping of direction, addition, subtraction of vectors, where subtraction is reframed as an addition problem by flipping the direction of the second vector. Then we also learn to decompose vectors into their components, which are along the I, j, and k axes. Then we learned how to perform vector addition and learn some very basic multiplication properties when working with the components of a vector. After which we went into the scalar product, which is essentially a projection of B onto A and then multiplying their magnitudes together along the same axis. We also went through some properties of dot product, such as orthogonality results in a zero dot product. After that, we went through the concept of projection vector, which is very, very similar to that of the dot product, because we are also dropping a right angle triangle and taking the distance if we want to find a projection length. If we want to find a projection vector, we essentially take the direction adjusted projection length, and we multiply it as a coefficient of the unit vector of B, such that we can get a vector that points along the axis of B. Then we went into planes, where we derived the parametric form. This one is not exactly important for machine learning, it's just there for understanding, where if you want to get any single point on the plane, you initially project onto the plane by using a known point A, after which you jump away from A by using any linear combination of real coefficients for two vectors, B and C, which are already assumed to be known to lie inside the plane. Next, we try to find the scalar product form of a vector plane by looking at it in terms of the scalar product, where we are essentially trying to find a collection of all possible arrows, where when we dot it to the normal, we project them onto the normal. Then we are trying to enforce the same distance. So no matter what our angle of our vector is like, it will always give the same distance from any point of our choice to the axis of the normal to the plane. So after we project it, the distance must always stay the same. And if we do that for the collection of all the points, it will map out the plane. Then we took that formula one step further by introducing the unit vector. So now once we use the unit vector, we have forced the magnitude of this thing to be 1. And therefore, when we do the scalar product, we do not change the size of the projection, because we are multiplying it by a magnitude of 1. Oh, I just realized that I missed this thing out here. Magnitude of 1. Okay. So that will give us the constant on the right, will therefore give us the orthogonal distance from the plane to the origin. Borrowing all these concepts, we try to relate it to the linear classifier, where assuming that we have a simple plane, we can actually use the polarity of the cosine of the angle between any new point and the normal to tell us whether the point lies to the left or to the right of the plane. And this is the basis for linear classifier. Okay, so what I've shown you here is the case for a plane that is centered about the origin. When I upload the notes later, I'll give you a case for when the plane is displaced away from the origin. So that means like this guy is actually like somewhere up here. All the same rules still apply. Okay, yeah. So, yeah, that's it for today. Any questions? Thanks all for bearing with me while I went over time a bit.
If you have no questions, you can leave.
Yes.
Okay, thanks.
Yeah.
If I can ask, how much of like chapter 7 exists?
Sorry? How much for chapter 7?
Oh. Yes.
I'll maybe put it around 1/3.
What the? Okay. 10.
Yeah.
GG.
Okay, bye guys.
Bye.
Right, thanks.
Bye.
Thanks.
Wait, just now at that point, isn't it more like...
Yeah?
Isn't it more like below the plane, not like to the left? Like if you scroll a bit, like D2, if like, because you said that plane is like projecting into and out of the screen, right? Then isn't D2 like more so like below rather than left? What do you mean by left?
Yeah, I mean in this case, because I was looking at it from the 2D point of view, so like over here is the left,
okay.
over here is the right. But you could also say below or above. In that case, like your eye will be like here, right? And you look at it this way.
Ah, okay.
Yeah.
Okay, thank you.
Yeah. Okay.